Welcome to an overview of logic. I'm IDK Math, and you can find me at mathIguess on most socials.
The aim of this paper is to autistically infodump about one of my special interests, so that strangers on the internet can enjoy my allegedly soothing voice while they fold laundry or sleep or the like. Or perhaps to help someone with logic here and there, I suppose. In this paper, we will be taking an introductory, informal look at logic. Specifically, we will discuss first-order logic, without caring for now about what the first-order part means. It is recommended that any reader or listener who particularly enjoys the content of this paper or this video takes a look at the source, which is in the bibliography of the paper. This is the source that I will use for most of the paper. It is a textbook by Susanna S. Epp, and it's called Discrete Mathematics with Applications. The version I was looking at said that it's the 5th edition, and it was published by Cengage Learning and printed in 2018, but there are different editions and different versions that are all really good for sure. When we want to acquire a new mathematical skill, it is helpful to keep the purpose of the skill in mind. The importance of logic, therefore, cannot be overstated. Logic, science, and philosophy are tied intimately together in the fact that mastery of these, or at least a subset of these, can aid us dramatically in our pursuit of truth. Hence, as we embark on our journey into the realms of logic and mathematics, it is critical that we remind ourselves that this will enable us to calibrate or perhaps install a sort of truth detector in our brains. And although brains are faulty and these detectors will never be perfectly reliable, a formalization of the concept surrounding truth will allow us to approach things with greater objectivity and precision. We ultimately want to be better at thinking and better at discerning fact from fiction, and learning logic will help with that. We begin by formalizing and condensing some notions that we intuitively understand before making sense of symbols that appear quite alien to a layperson. For the sake of this paper, we define a statement or a proposition to be a collection of words or symbols that we can meaningfully interpret to be true or false in a particular context. For now, we rely on the reader's intuition or the listener's intuition when it comes to the meaning of true and false. Such a statement will often be denoted by a single letter, usually P, Q, R, S, or maybe T. Some statements are called tautologies, and these are always true in the particular context provided, and we denote these by a capital T. The counterpart to this is a statement that's called a contradiction, which is always false, and therefore it's denoted by C for contradiction or F for false, depending on the textbook, of course. We define a term or an expression to be the so-called building block of the statements that we mentioned earlier. These are collections of words or symbols that might have some interpretable meaning, but not enough to the extent that we can say that they are true or false. These will turn out to be things like constants, variables, and functions of constants and variables. For now, we think of constants as like fixed values or numbers and names of specific entities, and variables are placeholder objects for those things. Functions are any means of connecting existing terms with other terms. We can think of something like plus or multiply in terms of functions. We note that relations are used to build statements from terms. These relations are usually called predicate symbols, and they take terms as an input and give us statements as an output. Functions are used to build terms from existing terms, and they're usually called function symbols. These take terms as an input and produce new terms as an output. It is assumed that equality is always a fair relation for us to use. So the equals sign that we are familiar with from high school is a symbol that we will always understand. This means that regardless of the underlying context or the universe of our discussion, we always understand what the equals sign means. The equals sign is something that we use to say that two terms have the same value in some sense. So we want to be able to say that two terms are essentially the same thing. But because we are also working with statements, we need to introduce a different symbol when we want to say that two statements are essentially the same thing. This is why we use something called a logical equivalence symbol, which we denote by a triple bar, in order to talk about logical equivalence. We now consider an example relating to terms and statements. We can let P be IDK is a goldfish, Q is IDK is a human, and R is 8 plus 5 equals 13. Additionally, we let S be 13 plus 48 minus 9. It is clear that in a literal sense, the first of these statements, IDK is a goldfish, is false, and Q and R, IDK is a human, and 8 plus 5 equals 13, are true. The loss of these, S being 13 plus 48 minus 9, is not a statement at all. It is just some number. We can calculate this number, but there's no meaningful way of saying whether it's true or false. Additionally, we can see that if IDK is a goldfish, then IDK is somehow not a human and the other way around. So there is some connection between those statements. This brings us to the point where we want to understand the connections between statements a bit better. We therefore introduce the idea of a connective. A connective is a symbol that denotes the action that is applied to a given statement or statements which gives rise to a new statement, with the exception of quantifiers for now. Negation is the act of changing the truth value of a given statement to the opposite truth value. Thus, if we are given a true statement, we can negate it and obtain a false statement. Negation is denoted by a tilde, or in some cases by more of a block symbol, which is just called the negation symbol. Conjunction is the act of combining two statements that are given in order to obtain a new statement that is true precisely when both of the given statements are simultaneously true. We denote this by a sort of wedge symbol, which looks like an upside down V. If we think about Q and R from earlier, which said that IDK is a human and 8 plus 5 equals 13, then the statement Q and R, or Q conjoined with R in other words, can be read as IDK is a human and 8 plus 5 equals 13, or something similar. Disjunction is the act of combining two given statements such that the resulting statement is false, precisely when both given statements are simultaneously false. We denote this with just a regular V, one could say. So if we have P and Q from earlier, which said that IDK is a goldfish and IDK is a human, respectively, then the disjunction of these two statements would be IDK is a goldfish or IDK is a human, or something similar. Implication. This is where we combine two given statements in such a way that the new statement is false only when the first statement that we were given is true and the second statement that we were given is false, simultaneously. We denote this by a rightward arrow, and we read it out loud as if P then Q, for example, if the given statements are P and Q. So if P and Q are as they were before, then we can say, if IDK is a goldfish, then IDK is a human, or something similar. We note that there are many other options here, but the above is plenty for our purposes. There are also two quantifiers that we work with in first-order logic. These are the existential quantifier, which is denoted by a backwards uppercase E, and the universal quantifier, which is denoted by an upside-down A. These will be important in the future, but we will only need them if this video is well received. Now that we know what statements and terms are, we are in a position where we can state what one thinks of as the foundation of our journey into logic and mathematics. Traditionally, philosophers only adopt three laws of logic, which they call identity, non-contradiction, and excluded middle. Very loosely speaking, these respectively say that a thing is itself, a thing can't be both itself and not itself, and a thing is either something or it isn't something. It is convenient for us as mathematicians to have plenty more laws than only these three, but we can justify these laws using truth tables, which we will talk about later. For those that need to memorize these laws, like I had to when I was studying logic, we just want to note that kadin diudanik b is a helpful mnemonic which will provide you with the first letter of each law. The laws are defined in the paper, however, I will just read their names out loud for the sake of the video. So there is a commutativity law, an associativity law, a distributivity law, identity laws, negation laws, De Morgan's laws, idempotent, or some people say idempotent laws, universal bound laws, a double negative law, some absorption laws, negations of tautologies and contradictions being the opposite of each other, an implication law, a contrapositive law, and then also a biconditional law, which sort of serves as a definition of a double arrow symbol, which I haven't mentioned before. We want to emphasize that there are no exceptions to the laws of logic, meaning that this is an excellent starting point for defining some sort of notion of objective truth, in the context of first-order logic especially. We are now in a position where we know what truth is, but we don't necessarily know how to evaluate it, which brings us to the next section. This is the section where we discuss validity and soundness. But in order to do that, we have to introduce the concept of an argument form. This is a set of premises, which are followed by a conclusion. We categorize argument forms using the concepts of validity and soundness, which we define next. An argument form is valid if the conclusion is forced to be true whenever all of the premises are true. We normally look at this using truth tables, as is done in our source, but that is not exactly audio friendly. We want to also note that an argument form that is not valid is invalid. An argument form is called sound if it is a valid argument form and all of the premises are true. If an argument form is not sound, then it is unsound. Unsound argument forms are such that truth values of one or more premise cannot be determined, or one or more premise contradicts with at least one other premise. The latter of these results in what's called a vacuously valid argument form, where the premises are never simultaneously true. So the conclusion's truth cannot force the argument to fail to be valid in some sense. There is a Latin phrase, pronounced roughly like ex falso sequitur quod libet, which is relevant here. It translates to something like, from falsehood anything follows. The key takeaway from this section is that sound arguments are valid, but valid arguments need not be sound, and invalid arguments are always unsound. In our pursuit of truth, we like valid arguments somewhat, and we like sound arguments a lot. Invalid arguments are just discarded, and unsound arguments require more refinement before they are of any use to us. This brings us to the inference rules. Metaphorically, we are now like trainee detectives that are aware that crime scenes can exist, but we don't have the power of deduction to tell us how to solve crimes from crime scenes. The inference rules will change that. For those that need to memorize these as I had to, we note that momo gespeset kako is a helpful mnemonic, giving us the start of each rule. We have modus ponens, modus tollens, generalization, specialization, conjunction, elimination, transitivity. Then the ka stands for cases, proof by division into cases, that is. And then we have a contradiction rule. Modus ponens says if you have the premises P implies Q and P, then you can conclude Q. Modus tollens says if you have the premise P implies Q and the premise not Q, then you can conclude not P. Generalization says if you have a premise P, then you can disjoin it to any other premise that you like. So we can conclude with P or Q. Specialization says that if you have a conjunction of two statements as a premise, P and Q for example, then you can conclude with only one of those two from that. So we can say, for example, we know that P and Q are simultaneously true, therefore P is true. Likewise, we can also say, therefore Q is true if we wanted to. Conjunction tells us that if we have two premises, P and Q, for example, then we can conclude P and Q. Elimination tells us that if we have a disjunction of two statements and one of them is known to be false, then we can get rid of that one and conclude with only the other one. So for example, if we have P or Q and not P, then we can conclude Q. Transitivity tells us that if you have P implies Q and Q implies R, you can conclude with P implies R, skipping the Q entirely. Proof by division into cases tells us if we have P or Q being true, and P implies R and Q implies R, we can already conclude R. We don't need to determine which one of those is true in some sense. And then lastly, the contradiction rule tells us that if not P implies a contradiction, we can conclude with P. We note that the inference rules are examples of valid argument forms, but as fallible creatures, we often fall prey to our intuitions. There are several well-known traps that one may fall into in this regard, which are what we call logical fallacies. These are invalid argument forms, or at least unsound arguments, that can bypass our critical thinking and tap into our emotion and intuition. This makes us accept statements as true when we really shouldn't accept them as true yet. The default position for any statement with an unknown truth value in our everyday life is generally to refuse to accept the statement as true until we become convinced otherwise. This is particularly true if we are skeptics. For further reading about fallacies, we urge the reader or the listener to go to the Wikipedia page called List of Fallacies. A pursuit of truth without comprehensive knowledge of valid rules of inference and awareness of common mistakes is doomed to fail before it even begins. It is important to note that a fallacy is specifically unreliable rather than being wrong. If they were reliably wrong, we could simply negate their conclusions to obtain valid argument forms. Next, we move on to giving the listeners or the readers homework if they want to. We avoided truth tables so far in this paper because it's supposed to be listenable. We will continue to avoid them for this reason, but it's important to note that a truth table can be constructed to mechanically verify whether a given statement is equivalent to another statement, and therefore whether it's a tautology or contradiction. Truth tables can also be constructed to verify whether a given argument form is valid or sound. We encourage the listener or the reader to explore truth tables on their own, since constructing a truth table really isn't that complicated, but it will likely be important in a future video if this video is received well. For completeness, I included a few examples of truth tables in the paper, so feel free to take a look if you're interested. Next, we look at some homework relating to the laws of logic. The laws of logic can be used to determine whether given statements are equivalent. These are akin to using operations like addition and multiplication to turn one expression into another expression in order to claim that those expressions are equivalent. We can apply the logical laws to turn a given statement into another statement to prove that they are equivalent. This is something that we again encourage the reader or listener to explore, since it might come up in a future video, and there are some examples in the paper. Lastly, for inference rules, we want to note that argument forms can be shown to be valid when using inference rules, but we normally rely on truth tables or even inspection to see whether a specific argument is sound or unsound. Again, we encourage the reader or the listener to familiarize themselves with applying inference rules so that future videos will not sound like some foreign language to them. There are a few examples of inference rules in the paper as well. Finally, we conclude. Logic need not be a difficult course, Possibly one of the trickiest things in logic is to adopt immense pedantry as one explores the topics, and this is because syntax is evaluated with laser-like precision by instructors. Common colloquialisms can become wrong, since we can no longer expect the examiners of our thoughts to meet us halfway. When I say something like, all cars are not blue, it's clear in any English-speaking context that I most likely mean to say, there exist cars that are not blue. However, a logician might interpret this more literally and suspect that I'm trying to say, no blue cars exist. This is the difference between all cars are not blue and not all cars are blue. If this video is received well enough, I will most likely create a follow-up. I hope that you've successfully folded a few shirts, washed a few dishes, fallen asleep, learned something along the way, or at least derived some entertainment from this. Thank you for watching.